Welcome to The Explainer. Today we're tackling a really mind-bending question. How do you actually measure complexity itself? We're going to dive into this idea of the ultimate zip file, the absolute shortest possible description for any piece of information, and see what it tells us about the very limits of what we can know. So let's start with a question that seems pretty simple on the surface. What makes something complex? Is it just about how it looks, how detailed and intricate it seems? Or is it something deeper, something about how difficult it is to actually describe? Okay, this slide is where things get really interesting because it totally flips our intuition on its head. On the left, you've got this gorgeous fractal. It looks like it has infinite detail, right? But you can generate that entire, seemingly complex image with a tiny little program, a super short recipe. Now look at the right. TV static. Looks simple enough, just a bunch of random noise. But there's no shortcut. There's no simple recipe. The only way to describe that exact pattern is to list out every single pixel, one by one. This whole idea gets even clearer when you look at it with text. So here we have two strings. String 1, well, you can see the pattern immediately. It's just AB over and over again. But string 2, it just looks like a completely random jumble of letters and numbers. There's no pattern there that we can see. And this right here, this is the core idea in a nutshell. The shortest possible way to describe string 1 is super short, right about 16 times, only 17 characters. But for string 2, well, the shortest description is just the string itself. You can't compress it. You can't simplify it. It has no hidden pattern. So in a very real, measurable way, string 2 is actually way more complex than string 1. So this insight brings us to a formal definition, one that was developed back in the 1960s by the brilliant mathematician Andrei Kolmogorov and a few others working independently. It's called Kolmogorov complexity. And all it is this. The complexity of a string, let's call it S, is just the length of the shortest possible computer program that prints out that string and then stops. That's it. It's the ultimate, most efficient description of that piece of information. Right, so the crucial point here is that we're using computer programs as our universal measuring stick. The true information content of anything, whether it's a string of text, a picture, even a song, is just the length of the smallest program you can write to generate it. Okay, so let's get right into this, because this is probably the first thing you're thinking. A program written in Python might be way shorter than the same program in, say, an older language like assembly, right? So how can this possibly be a universal measure if it depends on the language? It's a fantastic question. And the answer is something called the invariance theorem, and it's just a beautiful piece of logic. It says, yeah, the program lengths in different languages will be different, but they only differ by a fixed amount, a constant. And what is that constant? It's basically just the length of a small program that acts as a translator or an interpreter from one language to the other. So what this means is that when you're talking about really long, really complex strings, that little bit of extra length from the translator program becomes totally insignificant. It's like a drop in the ocean. The choice of language doesn't really matter. The complexity is a fundamental, objective property of the string itself. We've actually found a universal yardstick. But here's the first huge twist. Just as we found this absolutely perfect way to measure complexity, we run into a massive wall. It turns out this perfect ruler has a very, very big catch. I mean, it seems like we should be able to calculate it, right? We have a clear definition. So how would you actually go about finding the shortest program for any string you can think of? Well, the most logical way to do it would be just to search for it, a brute force approach. You could write a program that starts by generating every single possible program that's one character long. You run them all, check their output. If none of them work, you move on to all programs of length 2, then length 3, and on and on. Eventually, you're guaranteed to find one. And the very first one you find has to be the shortest. Simple, right? Except, well, it's not simple at all. There is a fatal flaw in this plan. What happens when you're testing one of these programs and it never stops? What if it's just stuck in an infinite loop, running forever? This brings us face to face with one of the most famous problems in all of computer science, the halting problem, proven by the great Alan Turing. It states that it's fundamentally impossible to write a single master program that can look at any other program and tell you for sure if it will eventually stop or if it will run forever. Because we can't solve the halting problem, our search might never end. We could be sitting there, waiting for a program to finish, and we'd have no way of knowing if it's just taking a very, very long time or if it's stuck forever. And that leads to a really staggering conclusion. The Kolmogorov complexity of a string is a well-defined number. It really exists mathematically, but it is uncomputable. We can never write a program that can, for every possible string, find it. So think about that. We've discovered a perfect ruler, but we can never actually read the measurement on it. This idea that some things are uncomputable isn't just a weird quirk of computer science. It actually leads to an even deeper, more profound implication, one that hits right at the heart of mathematics and the limits of what we can ever prove. So to get a feel for this, check out this classic little paradox. The phrase itself is supposed to define a number, the smallest positive integer that cannot be defined in fewer than 20 English words. But just count the words in that phrase. It's only 17 words long. So the definition itself violates its own rule. It's a contradiction. Well, a computer scientist named Gregory Chaitin took this exact kind of paradoxical thinking and applied it to Kolmogorov complexity. And what he found was absolutely stunning, and it tells us something deep about the limits of any formal system, including all of mathematics. So here's what Chaitin's theorem basically says. Take any formal system of logic, like the one that all of modern mathematics is built on. That system itself has a certain amount of complexity. Let's just call that complexity level L. The theorem proves that you can never use that system to prove that any specific string has a complexity greater than L. In short, a system cannot prove that something is more complex than itself. There's a kind of complexity ceiling, a horizon beyond which the system is completely blind. So, at this point, you might be thinking, okay, this is a fascinating philosophical puzzle, but is it just a puzzle? Does any of this actually matter in the real world? And the answer is yes, absolutely. These ideas have some surprisingly concrete connections. For starters, Kolmogorov complexity gives us the absolute theoretical limit for data compression. It literally defines the perfect zip file. It also gives us our best, most rigorous definition of randomness. A truly random string is one that's incompressible. Its shortest description is just the string itself. Some biologists even think that evolution might be guided by this principle, that it favors organisms with simpler, more compressible genetic programs because they're easier to build on and evolve. It's a pure, powerful measure of information. So, this whole journey to define something as simple as complexity has led us to these two absolutely profound limits. We found a perfect measurement that we can never actually calculate, and we found a horizon of proof beyond which our logical systems simply cannot see. And that leaves us with one last really provocative thought to chew on. We can easily prove that a string is simple by just showing the short program that creates it. But because of Chaitin's theorem, we can never formally prove that a string is truly complex, that it's truly random. All we can ever do is fail to find a pattern. So what does that mean for all the things we think are random in the universe? And what does it say about the true limits of our own knowledge?